In 2008, a computer engineer at a coal-fired power plant in Shanxi province, China, published a novel that contained the most accurate description of the universe ever written, and almost nobody noticed what he had actually done. His name was Cixin. He was 45 years old. He had been writing science fiction for over a decade, publishing short stories and novels in Chinese that had earned him a devoted following but almost no international recognition. His day job involved maintaining computer systems at the Niangziguan power station, a coal-fired facility in a mountainous region of northern China. He wrote at night. He had no academic affiliation in physics. He held no advanced degree in cosmology or thermodynamics. And the novel he published that year, The Dark Forest, the second volume in what would become the Remembrance of Earth's Past trilogy, contained a description of the universe's competitive dynamics that was more physically precise than anything a professional physicist had published in a peer-reviewed journal. You know the dark forest theory, or you think you do. Cixin laid it out across 400 pages of hard science fiction, and it goes like this. The universe is full of civilizations. They are all hiding, because the moment any civilization reveals its location, it gets destroyed by another civilization that cannot afford to take the risk that the newcomer might one day become a threat. 2 axioms. Survival is the primary need of civilization. Civilization continuously grows and expands, but the total matter in the universe remains constant. From those 2 premises, through a chain of logic involving the impossibility of interstellar trust and the unpredictability of technological development, Cixin derived a universe of silence, a cosmos where the rational move is to never speak, never signal, never reveal yourself, because the forest is dark and every civilization is a hunter, and if you make a sound, something will find you. The logic chain has 2 additional links that people often gloss over, but that matter enormously. The first is the chain of suspicion. Even if you are benevolent, you cannot know if another civilization is benevolent. Even if they are benevolent, they cannot know if you know they are benevolent. Even if they know you know, they cannot know what you think they think about what you think about them. The chain extends infinitely, and at every link, the cost of being wrong is extinction. At interstellar distances, where signals take years or centuries to travel, and where the biology and psychology of the other civilization may be beyond comprehension, the chain is, as the novel states, practically indestructible. The second link is the technological explosion. Human civilization has 5,000 years of recorded history, but modern technology emerged in roughly 3 centuries. On cosmic timescales, that is not gradual development. That is a detonation. A civilization currently inferior to yours could surpass you in a geological eye blink, which means no civilization can ever be safely dismissed as non-threatening. The primitive world you ignore today could be the superpower that destroys you tomorrow, and you would never see it coming because the timeline of technological development is not linear. It is exponential. It is, quite literally, explosive. It is a beautiful, terrifying piece of game theory. And when people discuss it, they discuss it as exactly that, game theory, a thought experiment about alien civilizations and strategic behavior, a fictional answer to Fermi's question about why the cosmos appears empty. You can find it on 100 YouTube channels and 1,000 Reddit threads, always framed the same way. What if aliens are hiding because the universe is dangerous? What if we should not be sending signals into space? What if SETI is a mistake? The discussion is always about aliens, about civilizations, about intelligent beings making strategic calculations across light years. That is not what it is. Cixin himself said something revealing on John Scalzi's blog in 2014 when The Dark Forest was being translated into English. He described his two axioms as the foundation of cosmic sociology and then added a curious qualifier about Axiom 2. He said it had not yet been proven by cosmologists. However, as a premise for a science fiction novel, he thought it was logically sound. The word however is doing enormous work in that sentence, because Axiom 2, the one about finite matter in an expanding universe, is not unproven. It is one of the most thoroughly established facts in physics. What Liu was being modest about, or perhaps coy about, was that he had not borrowed a literary conceit. He had restated a physical law. I have spent the better part of 2 months buried in this, reading papers across thermodynamics, information theory, bioenergetics, black hole physics, and ecology, and what I found is not what I expected. What Liu Cixin wrote is not a theory about aliens. His two axioms are not inventions. They are restatements, almost word for word, of experimentally confirmed physics that was published decades before his novel existed. Axiom 1. Survival is the primary need of civilization. That is what every dissipative structure in the universe must do to resist the second law of thermodynamics. Axiom 2. Total matter is constant, while civilizations expand. That is the finitude of free energy gradients, a consequence of entropy that has been understood since Rudolf Clausius coined the word in 1865. The chain of suspicion, the idea that interstellar trust is structurally impossible, that falls directly out of Landauer's principle, and the speed of light. The technological explosion is a measured empirical phenomenon that a Harvard astrophysicist named Eric Cixin has been tracking with hard data for 20 years. None of this is fiction. None of it is speculation. It is published, peer-reviewed, experimentally confirmed physics. And the fact that it has been sitting in the literature across 5 different fields for over a century without anyone connecting the pieces should frankly make you angry. And here is what should trouble you. There is nothing in the physics that limits this to civilizations. The axioms do not say anything about civilizations at all. They describe any organized system that needs energy to persist. But we will get to that. The question we need to answer first is simpler. If the dark forest is not fiction but physics, how deep does it go? How far down does the forest reach? And the answer, as it turns out, is much further than anyone wanted to look. To understand why, we need to start with a lunch. In the summer of 1950, at Los Alamos National Laboratory, 4 physicists walked to Fuller Lodge for lunch. Enrico Fermi, Edward Teller, Emil Konopinski, and Herbert York. They had been talking about a cartoon. The New Yorker had published a drawing by Alan Dunn on May 20th of that year, showing little green aliens stealing trash cans from a New York sidewalk. And the conversation had started with UFO sightings and drifted to the probability of extraterrestrial life. Somewhere between the appetizers and the main course, the topic shifted. And then Fermi, apparently out of nowhere, asked the question that has haunted astrophysics for 76 years. Where is everybody? Teller remembered it as exactly those words. York recalled it slightly differently. Konopinski had his own version. But all 3 agreed on the essentials. Fermi did a quick mental calculation right there at the table. about the number of stars in the galaxy, the probability of habitable planets, the likelihood of intelligent life, the time required for interstellar travel, even at a small fraction of the speed of light. And the numbers did not work. The galaxy is roughly 13 billion years old. Even at conservative estimates, a spacefaring civilization should have colonized the entire Milky Way in a few million years. That is a blink on cosmic timescales. So where is the evidence? Where are the signals? Where are the megastructures? Where is everybody? Fermi died of stomach cancer in 1954, never having published on the topic. The question outlived him, and for 76 years, every proposed answer has been some variation of the same move. In 1961, 11 years after Fermi's lunch, astronomer Frank Drake convened a small conference at the Green Bank Observatory in West Virginia to try to put numbers on the question. About 12 people attended, including Carl Sagan, who was 27 at the time, and Melvin Calvin, who received a phone call informing him he had won the Nobel Prize in chemistry while the meeting was still in session. They called themselves the Order of the Dolphin because one of the attendees, John C. Lilly, studied dolphin communication, and they figured if we could not understand dolphins, alien communication was going to be a challenge. Drake wrote an equation on a blackboard: n equals r star times f sub p times n sub e times f sub l times f sub I times f sub c times l. The number of detectable civilizations in the galaxy is the product of the star formation rate, the fraction of stars with planets, the number of habitable planets per star, the fraction where life emerges, the fraction where intelligence develops, the fraction that developed detectable technology, and the average lifetime of a communicating civilization. Otto Struve, the director of the observatory, raised his glass and said, "To the value of L, may it prove to be a very large number." Here is the thing about the Drake equation. It is not really an equation. It is a way of organizing ignorance. Every term after the first three was essentially unknown in 1961, and most of them remain poorly constrained today. The equation looks scientific. It has variables and multiplication signs, but plug in different estimates for f sub I or L, and you can get any answer from 0 to millions. It is a framework for thinking, not a tool for calculating. And the answers it has generated over the past 65 years reflect the assumptions of the people plugging in the numbers more than they reflect the universe. Robin Hanson proposed the Great Filter in 1996. His argument was different from most Fermi paradox discussions because it focused not on why we do not see aliens, but on what that absence implies about our own future. Somewhere between dead matter and galaxy-spanning civilizations, Hansen argued, there must be at least one evolutionary step of astronomically low probability, a great filter. And the terrifying question is whether that filter is behind us or ahead of us. If complex life is rare, the filter is behind us, and we are the lucky ones. If complex life is common but civilizations consistently self-destruct, the filter is ahead of us. And every time we discover that some precondition for intelligence, multicellularity, oxygen atmospheres, stable planetary orbits, is common in the universe, it pushes the filter forward in time. Finding alien microbes on Mars would be, from a Hansonian perspective, the worst news humanity could receive, because it would mean the filter is still ahead. But even Hansen's framework, clever as it is, assumes something specific about the nature of the filter. It assumes the filter is a barrier, a step that is hard to cross. What if the filter is not a barrier at all? What if it is a process? Not something civilizations fail to survive, but something that the physics of the universe continuously applies to any organized structure. Not a wall to climb over, but a pressure that never stops. Maybe civilizations are rare. Maybe they self-destruct. Maybe they are hiding. Maybe they are watching us like a zoo. Maybe the distances are too great. Every single answer assumes something about alien psychology, alien sociology, alien decision-making. Every answer treats the silence as a behavioral phenomenon, something that aliens choose to do or fail to do. I personally think that is the most underrated mistake in the history of science. Not the answers themselves, which are clever enough, but the assumption underneath all of them. The assumption that the silence requires an explanation rooted in choice. Because there is another category of explanation entirely, one rooted not in what civilizations decide to do, but in what physics requires them to do. And to see it, we have to go back further than Fermi, further than the space age, further than the 20th century. We have to go back to 1865, to a German physicist, and to the single most important equation ever written about the nature of reality, and to a man who hanged himself because nobody would listen to what it meant. There is a law that governs everything in the universe, not approximately, not metaphorically, everything. Every chemical reaction, every biological process, every star, every thought in your head, every civilization that has ever existed or ever will exist. And it says something very simple and very brutal. Disorder wins. Rudolf Clausius published the formal version in 1865. He had been working on the mathematics of heat engines, the kind of practical industrial problem that does not sound like it would overturn your understanding of reality. But Clausius found something universal hiding inside the engineering. He coined a word for it, entropy, from the Greek entropia, meaning transformation. And he summarized the two laws of thermodynamics in one sentence that should be tattooed on the inside of every physicist's eyelids. The energy of the universe is constant. The entropy of the universe tends to a maximum. That second part is the second law, and it means that in any closed system, things fall apart. Order dissolves into disorder. Hot things cool down. Structures crumble. Differences equalize. The universe moves relentlessly and irreversibly toward a state of maximum disorder, not because something pushes it there, but because there are overwhelmingly more ways for things to be disordered than ordered. It is statistics, it is probability, and it is absolute. Lord Kelvin put it differently in 1851. No cyclic process can convert heat entirely into work. There is always waste, always loss, always a tax paid to the void. Kelvin was trying to build better steam engines. What he found was the universe's most inviolable law. Think about what the second law actually says, stripped of the technical language. It says that every useful difference in the universe is temporary. Every hot spot will cool. Every concentration will dilute. Every gradient will flatten. The universe began in an extraordinarily low entropy state, tightly wound, all its energy concentrated in a point of almost inconceivable order, and it has been unwinding ever since. 13.8 billion years of unwinding. Stars burn, radioactive atoms decay, mountains erode, ice melts. Everything that happens, Every single process in the physical universe is part of this unwinding, and it only goes one direction. The second law is the arrow of time. It is why you remember the past and not the future. It is why eggs break but never unbreak. It is why you get older but never younger. It is the deepest asymmetry in nature. But here is where it gets worse. Because in 1877, a Viennese physicist named Ludwig Boltzmann wrote the equation that made this personal. S equals K log W. That is it. 5 symbols. It connects the macroscopic, the entropy you can measure with a thermometer, to the microscopic, the number of ways the atoms in a system can be rearranged without changing what it looks like from the outside. And it means that entropy is not some vague tendency. It is a precise, calculable quantity that tracks how many microstates correspond to a given macrostate. A melted ice cube has astronomically more microstates than an intact one. The glass on the floor has more microstates than the glass on the table. The math does not care about your preferences. It counts configurations, and the configurations that look like chaos outnumber the configurations that look like order by factors so large they do not have names in ordinary language. Boltzmann understood what this meant better than anyone alive, and it is worth pausing to say that it destroyed him. I do not mean that figuratively. He was born in Vienna in 1844, on the night between Shrove Tuesday and Ash Wednesday, and he later joked that this explained his wild mood swings. He was a big man, bearded, nearsighted, passionate about music and mathematics in roughly equal measure, and he spent the last 2 decades of his life in a war against some of the most powerful physicists in Europe. Ernst Mach, the philosopher-physicist who gave his name to the speed of sound, refused to accept that atoms existed. Atoms, he said. Have you seen one? Wilhelm Ostwald, the energeticist, insisted that energy was the only real physical quantity and that Boltzmann's statistical atoms were a fiction. At the 1895 meeting in Lübeck, Arnold Sommerfeld watched the two sides clash and later wrote that the struggle between Boltzmann and Ostwald resembled the battle of the bull against the flexible matador. But this time, the bull won. Except the bull did not survive the arena. Boltzmann's eyesight deteriorated until he could no longer read his own papers. His wife Henrietta had to write his manuscripts from dictation while an assistant read other scientists' work aloud to him. His eldest son died of appendicitis. He suffered from what we would now recognize as severe bipolar disorder. He lived, he told colleagues, in constant fear of losing his mind during a lecture. On September 5, 1906, while on vacation in Duino, a seaside town near Trieste, Ludwig Boltzmann hanged himself. His wife and youngest daughter had gone swimming. He left no note. The cruelty of the timing is almost unbearable. Albert Einstein's 1905 paper on Brownian motion had already provided the theoretical framework for proving atoms were real. Jean Perrin's definitive experimental confirmation came in 1908. Boltzmann died at the dawn of the victory he had been fighting for his entire career. The equation S equals K log W is carved on his tombstone in the Zentralfriedhof in Vienna. I have actually been there. It is a modest grave for a man who decoded the fundamental architecture of reality. Tourists walk past it to find Mozart and Beethoven. That feels about right. But here is what matters for our story. In 1886, 20 years before his death, Boltzmann gave a lecture that contains, as far as I can determine, the earliest statement of the thesis of this entire video. He said, and I need you to hear this carefully, that the general struggle for existence of living beings is not a struggle for raw materials, nor for energy, which exists in plenty in any body in the form of heat, but a struggle for entropy, which becomes available through the transition of energy from the hot sun to the cold earth. That is 1886, 122 years before Liu Cixin published The Dark Forest. Boltzmann had already identified what the dark forest is actually about. Not a struggle for matter, not a struggle for energy, a struggle for entropy, a struggle for the thermodynamic gradients that allow organized systems to exist. And nobody listened. The man who discovered the mathematical foundation of reality's deepest competition killed himself while the scientific establishment mocked his work. If that does not qualify as an abdication of authority, I do not know what does. Boltzmann's insight lay dormant until 1944, when Erwin Schrödinger, another Austrian physicist, dusted it off and made it vivid. In a series of lectures at Trinity College, Dublin, in February 1943, later published as the book What is Life, Schrödinger asked a question that biologists had been dodging for centuries. What is the physical basis of life? His answer drew directly on Boltzmann. What an organism feeds upon, Schrödinger wrote, is negative entropy. Every living system, from a bacterium to a blue whale, must continuously import low entropy energy, sunlight, food, chemical gradients, and export high entropy waste, heat, carbon dioxide, excrement, to maintain its organization against the second law's relentless push toward disorder. Life is not an exception to thermodynamics. It is a strategy for exploiting thermodynamic gradients, a temporary local reversal of entropy, paid for by a larger increase in entropy somewhere else. Leon Brillouin later shortened negative entropy to negentropy, which sounds like a startup, but is actually one of the most important concepts in physics, and Schrödinger's little book changed everything. Both James Watson and Francis Crick credited it with shaping their careers and their approach to the structure of DNA. The double helix, in a real sense, is a downstream consequence of Boltzmann's tombstone equation. But the story does not stop with Schrödinger, because in 1977, a Russian-born Belgian chemist named Ilya Prigogine won the Nobel Prize in Chemistry for proving something that sounds paradoxical on its face. He showed that far from equilibrium systems, systems being driven hard by energy gradients can spontaneously self-organize into complex structures. He called them dissipative structures, and the examples are everywhere once you know to look. Heat a thin layer of oil from below. At a certain temperature gradient, the fluid spontaneously organizes into hexagonal convection cells called Bénard cells, as regular and geometric as bathroom tiles. Nobody told the oil molecules to form hexagons. The gradient forced them into it. Mix certain chemicals together in specific concentrations, and you get the Belousov-Zhabotinsky reaction, where the solution oscillates between orange and blue in rhythmic waves that look alive even though they are nothing more than coupled chemical reactions exploiting an energy gradient. And life, Prigogine argued, is the same phenomenon at vastly greater complexity. A dissipative structure, an organized system that exists specifically because it dissipates energy more efficiently than the disorganized alternative. His popular book with Isabel Stenger's Order Out of Chaos, published in 1984 and translated into 18 languages made the case accessible. Order does not emerge despite the second law. It emerges because of it. The energy gradient between the hot sun and the cold vacuum of space creates conditions where matter self-organizes into increasingly complex structures, specifically because those structures are better at dissipating energy, at moving the universe toward maximum entropy faster. Think about what that means for a second. Really think about it. The universe does not tolerate complexity grudgingly. It generates complexity eagerly, because complex systems are more efficient entropy producers than simple ones. A forest dissipates solar energy more effectively than a bare rock. A city dissipates energy more effectively than a forest. You are not fighting the second law. You are an instrument of it. You exist because you are good at increasing disorder. That is your job. That is every living thing's job. And the better you are at it, the more the universe favors your existence. That is unsettling on its own, but it does not become the dark forest until you add one more piece. And that piece came from a young physicist at MIT who derived perhaps the most disturbing equation in modern science while on his honeymoon. Jeremy England was 29 years old in 2013 when he published a paper called Statistical Physics of Self-Replication in the Journal of Chemical Physics. What he did was apply the Crookes fluctuation theorem, a mathematical relationship between forward and reverse thermodynamic processes, to self-replicating systems. And what he found was a minimum bound on heat production during replication. The key insight is almost comically simple once you see it. Self-replication is thermodynamically favored in driven systems. Given a source of energy and a set of building blocks, the emergence of self-replicating structures is not miraculous. It is statistically expected. Life, England told Quantum magazine, should be as unsurprising as rocks rolling downhill. He actually derived the core equation during his honeymoon in Jerusalem in the summer of 2012. He was playing around with equations, flipping terms, and suddenly there it was, a relationship between entropy production and the probability of self-replication that nobody had noticed before. The implications went beyond theory. In 2017, researchers at MIT and elsewhere published computational results in PNAS, Statistical Physics of Adaptation, that provided the first concrete support for England's framework. They showed that systems of interacting particles, when driven by an external energy source, spontaneously develop configurations that absorb and dissipate energy more efficiently over time. The particles were not alive. They were not programmed to evolve. They were just particles in a field, following the laws of physics. And yet they self-organized into structures that got progressively better at absorbing energy from their environment. If that does not make the hair on the back of your neck stand up, you have not understood what it means. It means the arrow from simple to complex, from dead matter to self-replicating structure, is not a miracle. It is not even unlikely. It is what the physics predicts. Given sufficient energy in building blocks, complexity is the expected outcome. Life is what thermodynamics does with a good gradient. England also published Dissipative Adaptation in Driven Self-Assembly in 2015 in Nature Nanotechnology, showing that nanoscale particles driven by a periodic energy source spontaneously rearrange into configurations that absorb more energy from the driving force. The adaptation is happening at the most basic physical level. No DNA, no evolution, no biology, just matter, energy, and the Crookes fluctuation theorem. But here is the part of England's story that I find personally fascinating. He grew up in Boston, the son of a non-observant Lutheran father and a mother who was the daughter of Polish-Jewish Holocaust survivors. At his Harvard graduation, he was, by his own account, a committed atheist. Then during his Rhodes year at Oxford, he encountered hostility toward Israel that prompted him to explore his Jewish roots. And this is a man who went from avowed atheist to ordained Orthodox rabbi while simultaneously publishing some of the most important papers on the thermodynamic origins of life. He now teaches at Bar Ilan University in Israel and wrote a book called Every Life is on Fire that integrates thermodynamics with Torah. When asked about the contradiction, he said simply, "I do not myself see the contradictions. I bring this up not as a tangent, but because it matters for the argument. England is not a cold materialist reducing life to equations. He is someone who stared into the thermodynamic foundations of existence and found them, in his own words, sacred. The equations did not diminish meaning for him, they deepened it. You can decide for yourself what that tells you about what we are about to discuss, because here is what England's work means when you connect it to Boltzmann and Schrödinger and Prigogine. The second law does not just passively allow complex structures to emerge, it actively drives their emergence. Energy gradients create the conditions for self-organization. Self-replicating systems are thermodynamically favored. But, and this is the turn that makes the dark forest real, those gradients are finite. The sun will burn out. Chemical gradients deplete. Free energy is not infinite, which means multiple dissipative structures can and will emerge to exploit the same gradient. And when they do, they compete. Not because they choose to, not because they are aggressive or territorial or afraid, because the gradient cannot sustain them all. The more efficient dissipator wins, the less efficient one is excluded, not by violence necessarily, by the mathematics of entropy production. This is not a theory about alien civilizations. This is the second law of thermodynamics applied to organized complexity. Competition is not a behavior, it is a physical inevitability, and it has been operating since the first convection cell formed in the first pool of cooling matter after the Big Bang. Lou Cixin's Dark Forest is not science fiction. It is Boltzmann's 1886 lecture with better marketing. And the fact that it took 122 years for someone to spell this out, and that the someone was a coal plant engineer writing novels at night, and not the global physics establishment, is something that should bother you deeply. But that is still not the disturbing part, because everything we have discussed so far assumes the competition is about energy, about free energy gradients and entropy production. And that is true as far as it goes. But there is another resource in the universe that is even more fundamental than energy, one that turns out to be even more scarce, and its scarcity is not a feature of our current understanding. It is a law of nature that was proven by a man who had every reason to understand what erasure really means. Rolf Landauer was 11 years old when his family fled Stuttgart for New York in early 1938. He was Jewish. His father had served the Kaiser in the First World War, had been severely wounded, had received an Iron Cross, and was, by every account, an ardent German nationalist who believed until the very end that the Nazi regime was just a temporary aberration. He died of his war wounds in 1934, leaving a letter asking that his sons be raised as good Germans. 4 years later, the good Germans were burning synagogues. The family got out just in time. Young Rolf graduated from Stuyvesant High School at 16, completed Harvard in 2 years, skipping every other math course and passing on examination alone, served in the Navy as an electrician's mate, earned his PhD from Harvard in 1950, and joined IBM Research in 1952. He spent the next 4 decades there, becoming an IBM Fellow in 1969, one of the company's highest technical honors. Colleagues described him as a man of sometimes brutal honesty, irascible but kindly. He published over 200 papers, and in 1961, he wrote the one that changed everything. The paper was called Irreversibility and Heat Generation in the Computing Process, published in the IBM Journal of Research and Development. And it proved something that sounds almost absurdly specific, but turns out to be cosmically important. Erasing one bit of information costs a minimum amount of energy. That minimum is K times T times the natural log of 2. At room temperature, about 300 Kelvin, that works out to roughly 2.87 times 10 to the negative 21 joules. That is a stupendously small number, and it is absolutely inescapable. Here is why. A bit can be 0 or 1, 2 states. When you erase it, you are forcing it into a single known state. You are performing a many-to-one mapping. Before erasure, the bit occupied 2 possible microstates. After erasure, it occupies 1. The system's entropy has decreased by k log 2, and by the second law, that entropy cannot just vanish. It must appear somewhere else, as heat dissipated into the environment. You cannot erase information without paying a thermodynamic price. I need to pause on that, because it sounds like a technicality, and it is not. What Landauer proved is that information is physical, not metaphorically physical, not usefully analogous to physical, physically physical. Information exists only through physical representation. He wrote in a 1991 paper bluntly titled Information is Physical, published in Physics Today. It is tied to all the restrictions and possibilities of our real physical universe. Now, here is where people get this wrong, and I spent about 3 hours going down this rabbit hole before I understood the subtlety. Dozens of YouTube videos and pop science articles will tell you that Maxwell's demon violates the second law. It does not. Charles Bennett proved in 1982 that the demon's entropy cost comes not from measuring molecules, but from erasing its memory. The measurement is thermodynamically free. It is the forgetting that costs you. The demon has to clear its memory to make room for new measurements. And that clearing process, that erasure, generates exactly enough heat to compensate for any entropy reduction the demon achieved. The books balance. They always balance. Bennett's insight actually overturned part of Landauer's original framework. And here is something I love about this story. When Bennett, a younger colleague at IBM, published results that essentially corrected his mentor's analysis, Landauer responded not with defensiveness, but with genuine curiosity. He engaged with the new ideas seriously and graciously. In a field where egos are as fragile as quantum states, that matters. But Landauer's principle had a problem. For 51 years, nobody could confirm it experimentally. The energy involved, 10 to the negative 21 joules per bit, is so small that measuring it requires extraordinary precision. The thermal noise at room temperature drowns it out. The principle sat in the literature, theoretically solid, but experimentally unverified. And in physics, unverified means unfinished. That changed on March 8, 2012, when Antoine Barroux and colleagues at the École Normale Supérieure in Lyon published a paper in Nature called Experimental Verification of Landauer's Principle, Linking Information and Thermodynamics. What they did was elegant. They trapped a 2 micrometer silica bead, a tiny glass sphere about the size of a large bacterium, in a double well potential created by focused laser beams at a wavelength of 1064 nanometers. The 2 wells represented the 2 states of a bit, 0 and 1. They erased the bit by lowering the barrier between the wells, applying a tilting force to push the bead into one well, and then raising the barrier again. Over hundreds of erasure cycles, they measured the heat dissipated into the surrounding water. The result was exact. The mean dissipated heat converged on kT times the natural log of 2 in the slow erasure limit. The Landauer bound was confirmed. Individual erasure events could fall below the limit due to thermal fluctuations, but the average never did. The paper explicitly noted that this limit is independent of the actual device, circuit, or material used. It is universal. It is physics. And the complementary experiment had actually come 2 years earlier. In 2010, Shoichi Toyabe and colleagues published in Nature Physics a demonstration of the reverse process. Using a dimeric polystyrene particle rotating in a spiral staircase potential, they built a functioning Szilard engine that converted information about the particle's position into actual mechanical work. They extracted 0.28 kT log 2 of energy per bit of information, more than a quarter of the theoretical maximum. This was the first experimental proof that information about a system's microscopic state can be used to extract useful work from thermal noise. Information is not just physical, it is fungible with energy. Since then, the experimental confirmations have accelerated. Koski and colleagues at Aalto University built a single electron Szilard engine in 2014. In 2015, the same group built an autonomous on-chip Maxwell's daemon, where both the system and the daemon's thermodynamics were simultaneously measurable. And in 2025, Ahmet and colleagues published in Nature Physics the first test of Landauer's principle in quantum many-body systems, using ultra-cold Bose gas quantum field simulators. The principle holds at every scale tested so far: classical, quantum, single particle, many-body. It is as fundamental as the second law itself, because it is a consequence of the second law. Now, what does this have to do with the dark forest? Everything. Because what Landauer proved is that every act of information processing, every observation, every computation, every prediction, every model of the environment has an irreducible thermodynamic cost. It does not matter if you are a human brain, a silicon chip, a quantum computer, or an alien intelligence based on physics we have not imagined yet. If you process information, you pay in energy. If you erase information to make room for new information, you pay in energy. If you observe your environment to check for threats, you pay in energy. A 2024 paper in the Proceedings of the National Academy of Sciences, authored by 19 researchers, led by David Wolpert, titled "Is Stochastic Thermodynamics the Key to Understanding the Energy Costs of Computation?" put concrete numbers to this across domains. They found that biological systems are approximately 100,000 times more energy efficient than current human-built computers. DNA replication operates at only about 165 times the Landauer bound. Protein translation runs at about 20 times the Landauer bound. Our best silicon chips run at millions of times the Landauer bound. Biology, in other words, has had 4 billion years to optimize toward the thermodynamic flaw, and it is still not there. The flaw is real, the cost is real, and every computational system in the universe is paying a premium above that flaw that it can never entirely eliminate. This means information processing systems are not just competing for raw energy, they are competing for the energy required to know things. Knowledge itself is a finite, physically costly resource. Every prediction you make about the future costs energy. Every model you maintain of your environment costs energy. Every memory you store costs energy, because maintaining a memory against thermal noise requires continuous error correction, which requires erasure, which requires energy per Landauer. The chain of suspicion in Liu Cixin's Dark Forest, the idea that you can never verify another civilization's intentions because communication takes too long and costs too much, is not a game-theoretic convenience. It is a thermodynamic fact. Every signal sent costs energy. Every signal received must be processed, which costs energy. Every model of another civilization's behavior maintained in your memory costs energy. And at interstellar distances, with light-speed communication delays spanning years or centuries, the cost of maintaining accurate models of other civilizations' intentions exceeds any possible benefit, because the models are always out of date by the time you use them. You are paying Landauer's tax on information that is already obsolete by the time you receive it. The Dark Forest's chain of suspicion is Landauer's principle applied across light years. It is not sociology. It is information physics, and the irony of Landauer himself should not be lost here. A man whose family fled the systematic erasure of Jewish identity from Europe discovered the fundamental physical cost of information erasure. A man who was told by his dying father to be a good German found that forgetting has a minimum price that the universe itself enforces. You cannot erase anything for free. Not a bit. Not a memory. Not a people. The universe charges you for every deletion in the only currency it accepts: heat, disorder, the forward march of entropy. Landauer died of brain cancer on April 27, 1999, at 72. His principle had been ignored for decades. It is now recognized as one of the foundational results in the physics of information. But even Landauer did not see the full picture, because the cost of information is only half the problem. The other half is the supply. And the supply, it turns out, has a ceiling, a hard, absolute, physically inescapable ceiling. And the man who found it was a graduate student with the audacity to challenge the most famous physicist alive. The story begins, like so many important things in physics, with a cup of tea. Jacob Bekenstein was born on May 1st, 1947, in Mexico City to Polish Jewish immigrants who had met there during the chaos of the Second World War. He was the kind of kid who launched model rockets inspired by Sputnik and stayed up late reading about black holes. By the early 1970s, he was a graduate student at Princeton, working under John Archibald Wheeler, one of the titans of general relativity, and the man who had coined the term black hole. One afternoon, over tea, Wheeler posed a question that that sounded like a thought experiment, but turned out to be a crack in the foundations of physics. What would happen, Wheeler asked, if you poured a hot cup of tea into a black hole? The tea has entropy, quite a lot of it in fact. But once it crosses the event horizon, it is gone, lost to the outside universe, which means the total entropy of the observable universe just decreased, which means the second law of thermodynamics just broke. Most students would have filed this under interesting problems for later. Bekenstein did not. He proposed, in his 1972 PhD thesis and a 1973 paper titled Black Holes and Entropy in Physical Review D, that black holes themselves have entropy, that the entropy is proportional to the area of the event horizon, that when you throw tea into a black hole, the horizon grows, the black hole's entropy increases, and the second law is saved. Fellow student Robert Wald later said the project was considered foolhardy. Stephen Hawking was furious. At a 1972 conference in France, Hawking and several senior colleagues confronted the young Bekenstein. These three were senior people, Bekenstein later recalled. I was just out of my PhD. You worry whether you are just stupid and these guys know the truth. Hawking's objection was precise and on the face of it, devastating. If a black hole has entropy, it must have a temperature. If it has a temperature, it must radiate. But nothing escapes a black hole. Therefore, Beckenstein was wrong. The argument was airtight, except it contained a hidden assumption. Hawking was assuming that the event horizon was a perfect classical boundary. And in quantum mechanics, there are no perfect boundaries. Hawking went home and did the calculation. What he found stunned him. Quantum effects near the event horizon, specifically the production of virtual particle pairs where one particle falls in and the other escapes, cause black holes to emit thermal radiation at a temperature given by h bar times the surface gravity divided by 2 pi times Boltzmann's constant. Black holes do radiate. They do have temperature. They do have entropy. Beckenstein was right about everything. The student had seen deeper than the master. The resulting equation, S equals K times A divided by 4 times the Planck length squared, is carved into the foundations of modern physics. It is the first equation in history to contain all 4 fundamental constants: the gravitational constant, the speed of light, Planck's constant, and Boltzmann's constant. It connects quantum mechanics, gravity, thermodynamics, and information in a single expression. Hawking later said he wanted it on his tombstone. I personally think it is the most beautiful equation in physics. Not because it is simple, though it is, but because it says that information, that most abstract and seemingly immaterial of things, is carved into the geometry of space-time itself. The boundary of a black hole does not just contain matter and energy. It contains information, and the amount of information it can contain is finite, calculable, and determined by the area of the horizon in Planck units. Beckenstein was gracious about the vindication. I wrote it down first, he said. Hawking found the numerical value of the constant. Together, we found the formula as it is today. He was a deeply religious man who wore a kippah and once said, "I look at the world as a product of God." He set very specific laws, and we delight in discovering them through scientific work. He won the Wolf Prize in 2012 and the Israel Prize in 2005. And on August 16, 2015, at age 68, he died of a sudden heart attack while attending a conference in Helsinki, months after receiving the American Physical Society's Einstein Prize. Lee Smolin called his discovery among the most fundamental in theoretical physics. But it was Beckenstein's 1981 paper that matters most for our story. Universal upper bound on the entropy to energy ratio for bounded systems, published in Physical Review D. In it, he proved that the maximum information content of any region of space is bounded by a specific formula involving the region's radius and total energy. The proof is beautiful in its simplicity. If a system violating the bound existed, you could lower it into a black hole and violate the second law. Since the second law cannot be violated, the bound must hold. Black holes saturate the bound. They contain the maximum possible information for a given size and energy. Nothing can contain more. And the bound is shockingly restrictive. Gerard 't Hooft extended this in 1993 in a paper called Dimensional Reduction in Quantum Gravity, showing that the total degrees of freedom in any region of space cannot exceed 1/4 of the boundary's surface area, measured in Planck units. Leonard Susskind formalized this as the holographic principle in a 1995 paper titled The World as a Hologram, published in the Journal of Mathematical Physics. The three-dimensional world of ordinary experience, Susskind wrote, is a hologram, an image of reality coded on a distant two-dimensional surface. Now, you have probably heard that the holographic principle means we live in a hologram, like the Matrix. That is not what it means. What it means is that the information content of a volume of space is not proportional to the volume. It is proportional to the surface area. This is profoundly strange. If you double the radius of a room, you get 8 times the volume, but only 4 times the surface area. The information capacity grows more slowly than the space it occupies. The universe is not fake. It is weirder than fake. The information that defines reality has a geometry, and that geometry has a ceiling. Seth Lloyd at MIT put numbers to this ceiling in 2002 in a paper called Computational Capacity of the Universe, published in Physical Review Letters. Using the Margulis-Levitin theorem, which bounds computational speed by energy, and the Bekenstein bound, which bounds information by energy and size, Lloyd calculated the universe's total computational budget, maximum operations performed since the Big Bang, approximately 10 to the 120th. Maximum bits stored by conventional matter, approximately 10 to the 90th. 10 to the 90th bits. That is the universe's hard drive. That is all the information that all the matter in the observable universe can contain. Those sound like absurdly large numbers. They are not, relative to the demands placed on them. Consider that a single human brain contains roughly 100 billion neurons, each with up to 10,000 synaptic connections. The total informational content of a human brain has been estimated at around 2.5 petabytes, roughly 10 to the 16th bits. A single civilization of 8 billion such brains already represents a significant draw on the local information budget. Now multiply by the billions of potentially habitable planets in the Milky Way alone. Now multiply by the hundreds of billions of galaxies in the observable universe. 10 to the 90th is a large number, but it is not infinite. And infinity is what you need for there to be no competition. Lloyd's core thesis, elaborated in his 2006 book, Programming the Universe, is stark. All physical systems register and process information. The laws of physics determine the amount of information that a physical system can register and the number of elementary logic operations that a system can perform. The universe is a physical system. That last sentence should disturb you, because it means the universe is not just a place where information processing occurs. It is itself an information processing system, with finite computational resources running a finite number of operations on a finite number of bits, and everything that exists within it, including you, including every civilization that has ever existed, is competing for a share of those resources. And this is where the black hole information paradox becomes more than an academic curiosity. When Hawking published his 1975 paper on particle creation, he discovered that the radiation emitted by evaporating black holes is thermal, random, featureless. It carries no information about what fell in, which means that when a black hole fully evaporates, all the information about everything it ever consumed is destroyed. A pure quantum state becomes a mixed state. Unitarity, the bedrock principle that information is never truly lost in quantum mechanics, is violated. This tortured theoretical physics for 40 years, the black hole information paradox. Hawking himself bet John Preskill a set of encyclopedias that information was truly destroyed, then conceded the bet in 2004, presenting Preskill with a baseball encyclopedia in a ceremony at a physics conference. Though even Hawking's proposed resolution was not widely accepted at the time, the problem was simple to state and seemingly impossible to solve. If information goes into a black hole and the radiation coming out is random, where does the information go? Quantum mechanics says it cannot be destroyed. General relativity says it cannot escape. One of them has to be wrong, or both of them have to be modified. The greatest minds in theoretical physics spent decades trying to find a way out. The breakthrough came in May 2019. Two papers appeared almost simultaneously. Jeffrey Pennington published Entanglement Wedge Reconstruction and the Information Paradox. Ahmed Almhiri, Netta Engelhardt, Donald Maroff, and Henry Maxfield published a complementary result. Using the quantum extremal surface prescription, they derived the page curve, proving that black hole evaporation does respect unitarity. Information is not destroyed. The key mechanism involves what they called islands, regions inside the black hole that become quantum informationally connected to the external radiation. After a critical moment known as the page time. Before the page time, the entanglement entropy of the radiation increases as more particles escape the black hole. After the page time, it decreases, following a curve first proposed by Don Page in 1993. The island formula shows that these interior regions contribute to the radiation's entanglement structure in a way that preserves information even as the black hole shrinks. Later that year, replica wormhole calculations by two groups provided the gravitational path integral justification, showing that certain space-time geometries, wormholes connecting different copies of the system, dominate the calculation and enforce unitarity. Donald Maroff called it the most exciting thing that has happened in this subject since Hawking. The result was not just a resolution of a theoretical puzzle. It was a declaration about the nature of information in the universe. Information is conserved. It has physical reality. It obeys thermodynamic laws. It cannot be created or destroyed without consequence, and it is finite. The universe keeps its books. Every bit matters. Every erasure has a cost. Every piece of information that enters a black hole persists in some form, encoded in the quantum correlations of the radiation. Nothing is truly lost. But nothing is free either. So now we have two finite resources, free energy as established by the second law, and information capacity as established by the Beckenstein bound. Both are physically real. Both are scarce. Both are required by any system that wants to persist against entropy, because persisting requires modeling your environment, which requires information processing, which requires energy. If information capacity is finite and information processing costs energy, then every system that models its environment is drawing from the same finite account. Not just civilizations, every cell, every ecosystem, every neural circuit in your brain. The dark forest might not be between species out there. It might be the operating system of reality at every scale, but that is a conclusion we are not ready for yet. Because there is one more piece of evidence that needs to be examined, and it comes not from cosmology or information theory, but from a place you would not expect, ecology. And from there, from the strangest neuroscientist alive. In 1934, a Russian biologist named Georgy Gauss published a book called The Struggle for Existence. And in it, he described an experiment so simple and so devastating that biology has been arguing about it ever since. He grew two species of paramecium, single-celled organisms about the size of a grain of sand, Paramecium aurelia and Paramecium caudatum. He grew them separately. Both species thrived. They ate the same bacterial food, occupied the same kind of space, reproduced at healthy rates. No problems. Then he grew them together. Same food source, same space, same conditions. P. aurelia 1. Every time. Not because it was more aggressive, not because it attacked P. caudatum or developed some kind of weapon, but because it was approximately 5% more efficient at consuming the shared resource. That 5% compounded across generations until P. caudatum was gone. Extinct, not violently, thermodynamically. The experiment is almost boring in its simplicity, which is exactly why it is terrifying. There is no drama, no conflict, no predation. Just two populations, one shared resource, a tiny efficiency differential, and time. Time does the rest. The less efficient user of the gradient declines slowly, almost imperceptibly, generation by generation, until it crosses the threshold below which its population cannot sustain itself. And then it is gone. Gauss ran the experiment multiple times with different species pairs. The result was the same. He stated it as a principle. Complete competitors cannot coexist. Two species occupying the same ecological niche, exploiting the same resource in the same way, cannot stably share that resource. One will always outcompete the other. The more efficient user of the gradient wins. Always. Given enough time. I have been obsessed with this experiment since I first encountered it in graduate-level ecology papers. Because the more I looked into it, the more I realized Gauss had accidentally demonstrated a principle that extends far beyond biology. He thought he was describing a rule about paramecia. He was describing a rule about the universe. The principle has been confirmed in hundreds of ecological studies since 1934. Joseph Hardin formalized it in 1960 as the competitive exclusion principle. The exceptions, cases where two species apparently do coexist on the same resource, always turn out on closer examination to involve some form of niche differentiation. The species are not actually complete competitors. They partition the resource in time, space, or chemical specificity. When two species truly compete for identical resources in identical ways, one wins, always. And here is the part that does not get discussed enough, that I think is quietly the most important implication of this entire line of research. The principle does not require biological competition. It does not require DNA, or cells, or natural selection in the Darwinian sense. It requires only three things: a finite resource, two or more systems consuming that resource, and a difference in efficiency between them. That is it. Three conditions, and all three are guaranteed by the second law of thermodynamics, applied to any universe with finite free energy gradients, which means competitive exclusion is not a biological phenomenon that happens to have physics underlying it. It is a physical phenomenon that happens to have biology as its most visible expression. In 2021, a paper published in the journal Entropy demonstrated winner-take-all attractor dynamics in stochastic chemical reaction networks. When driving concentration gradients decrease, only the states with bifurcation processes of sufficient thermodynamic efficiency can retain their stability. This is competitive exclusion at the molecular level, not between organisms, between chemical structures, between patterns of matter organized by energy flow. Other research has shown that the Lotka-Volterra two-species competition model, the mathematical framework ecologists use to describe competitive exclusion, reduces to the Frank model for chemical competition between mirror image molecules called enantiomers. The mathematics of ecological competition and the mathematics of chemical selection are the same mathematics. Eric Schneider and James Kay proposed in the mid-1990s that the second law can be restated as a tendency for systems to resist applied gradients, and the further a system is pushed from equilibrium, the more sophisticated the mechanisms it develops for that resistance. Applied to competitive exclusion, this means the competition intensifies as the energy gradient increases. More energy drives more complex structures, which compete more fiercely for the gradients that created them. Now enter the strangest neuroscientist alive. Carl Friston was born on July 12, 1959. He is the scientific director of the Wellcome Centre for Human Neuroimaging and University College, London. He is the most cited neuroscientist in history, with an H-index exceeding 280 and approximately 400,000 total citations. He invented statistical parametric mapping, the software used in over 90% of brain imaging studies, and he publishes roughly one paper every 4 days. 85 papers in 2017 alone, over 1,800 total. The philosopher Maxwell Ramstead said that upon first understanding Friston's framework, he almost had a nosebleed. Friston arrives at UCL's Queen Square at 12:25 each afternoon. He smokes in the garden by the statue of Queen Charlotte. He communicates with his wife and 3 sons before noon, according to a 2018 Wired profile, via an agreed-upon series of smiles and grunts. His papers are so notoriously impenetrable that it is a running joke in neuroscience that only Friston can really understand them. When I first tried to read a free energy principle for a particular physics, his 2019 monograph, I got through about 12 pages before realizing I had been reading the same paragraph for 20 minutes. It is dense in the way that general relativity is dense. Not because the ideas are poorly expressed, but because each sentence depends on technical machinery that takes years to build up, and his central idea might be the most important theoretical framework proposed in the 21st century, or it might be unfalsifiable philosophy disguised as mathematics. The jury is genuinely still out. His scientific origin story involves watching woodlice as a child. He noticed that the tiny crustaceans moved faster in warm areas and slower in cool ones. The conventional explanation was purposeful behavior, that the woodlice were seeking cool, dark environments suitable for survival. But Friston saw something different. The movement had no purpose. The woodlice were not seeking anything. They simply moved faster when warm and slower when cool. And the statistical result was that they accumulated in cool places. All these contrived, anthropomorphized explanations of purpose and survival and the like all seemed to just peel away, he later said. And the thing you were observing just was, in the sense that it could be no other way. That phrase, "it could be no other way," is the emotional core of the free energy principle. And it is the emotional core of the dark forest. The free energy principle, first formally proposed in 2005 and given its landmark treatment in a 2010 Nature Review's neuroscience paper titled The Free Energy Principle, a unified brain theory, states that any self-organizing system that persists over time must minimize variational free energy, a computable upper bound on surprisal. In human terms, that means any system that exists must avoid states that are incompatible with its continued existence. A fish in water is in an unsurprising state. A fish on a sidewalk is in a very surprising state. The fish will not last long on the sidewalk. Systems that persist are systems that have found ways to minimize surprise, either by updating their internal models to better predict their environment, which Friston calls perceptual inference, or by changing the environment to match their predictions, which he calls active inference. This is where it gets relevant to the dark forest, because Friston's most ambitious claim is that the free energy principle is universal. In a 2013 paper titled Life as We Know It, he argued that biological self-organization is an inevitable and emergent property of any random dynamical system that possesses a Markov blanket, a statistical boundary separating inside from outside. In a massive 2019 monograph, A Free Energy Principle for a Particular Physics, he extended this to all distinguishable systems, from rocks to rock stars, as he put it. If this is correct, and I want to be honest that there is significant debate about whether it is, then every self-organizing system that persists in the universe does so by modeling its environment and acting to minimize surprise. In a universe with multiple self-organizing systems, the most potent source of surprise is other self-organizing systems. They are unpredictable. They are complex. They are competing for the same gradients, which means that in a multi-agent environment, the free energy principle would demand that every persistent system develop some form of threat detection and response. Not because it chooses to, because minimizing surprise in the presence of other agents requires it. Critics have raised serious objections. Beal, Pollock and Kenai published a 2021 paper in Entropy, finding that crucial mathematical steps in the original argument are not generally correct without additional unstated assumptions. Bruinberg and colleagues argued in 2022 that the Markov blanket concept has been stretched beyond its technical definition. The pebble problem persists. If the principle applies to everything, does it explain anything? I do not want to pretend these objections are trivial. They are not. Friston's framework might be a profound truth about self-organization, or it might be a mathematical tautology that applies to everything and therefore predicts nothing. Time and further experiment will tell. But even the conservative reading of Friston's work supports the dark forest thesis. At minimum, any biological system that persists must have some mechanism for detecting and responding to environmental threats, including other organisms. That is not the free energy principle. That is just evolution by natural selection. And evolution by natural selection is a thermodynamic process driven by differential efficiency in energy utilization, which is competitive exclusion, which is Gauss's principle, which is the second law. The thread connects. Thermodynamic gradients drive self-organization. Self-organization produces competing structures. Competing structures must model each other, which costs energy per Landauer. The more efficient modeler wins per Gauss. The losing structure is excluded, and the information capacity for all this modeling is capped by the Beckenstein bound. Take a step back and look at what has happened. We started with a science fiction novel about aliens. We have arrived at a chain of experimental results and mathematical proofs, each one published in a major journal, each one independently confirmed, each one considered settled physics in its own field, that together describe a universe where competition between organized structures is not optional. It is not cultural. It is not a phase civilizations go through and then transcend. It is the mathematical consequence of finite energy, finite information, and the second law. No amount of wisdom, compassion, or advanced ethics changes the physics. A civilization of saints and a civilization of monsters face the same Carnot limit, the same Landauer cost, the same Bekenstein bound, the same thermodynamic imperative to import free energy and export waste heat. The dark forest is not about morality, it is about mathematics. The dark forest operating at every scale. Now bring in Eric Cicin's data. Cixin, at the Harvard-Smithsonian Center for Astrophysics, has spent decades measuring what he calls energy rate density, the free energy flow per unit mass per unit time across the entire sweep of cosmic history. The numbers form a staggering progression. Galaxies sit at roughly half an erg per second per gram, stars at about 2, Earth's geosphere at about 75, plants at around 900, animals at roughly 40,000, the human brain at about 150,000, modern civilization at approximately 500,000. The pattern is exponential. Each level of complexity processes energy per unit mass faster than the last by orders of magnitude. Cultural evolution is steeper than biological evolution, which is steeper than physical evolution. Complexity does not just grow, it accelerates. This is Cicin's central insight, published in multiple papers and books, including Cosmic Evolution in 2001 and a 2011 paper in Complexity titled Energy Rate Density as a Complexity Metric and Evolutionary Driver. Let me put the numbers in perspective, because they deserve it. A typical galaxy processes about half an erg per second per gram. The Sun processes about 2. So far the increases are modest, factors of 2 and 4. But then you get to Earth's geosphere at 75, almost 40 times the Sun, plants at 900, 12 times the geosphere, animals at 40,000, 44 times plants, the human brain at 150,000, nearly 4 times a typical animal, and modern human civilization at roughly 500,000, more than 3 times the brain. The acceleration is the point. Each transition does not just add capacity, it multiplies it. And the jumps are getting bigger and faster. It took billions of years to go from stars to plants, hundreds of millions to go from plants to animals, tens of millions to go from early mammals to primates, a few 100,000 to go from early humans to civilization, a few centuries to go from pre-industrial civilization to the current energy density. The curve bends upward, steeper and steeper. Whatever comes next will be another jump, and it will happen faster than the last one. This is Cixin's technological explosion measured in real data. The unpredictable rate at which civilizations can grow in capability is not a fictional conceit. It is an empirical fact about how energy rate density scales with complexity. Civilizations do not grow linearly. They explode, which means any assessment of another civilization's threat level is obsolete almost immediately, because their energy rate density could jump by orders of magnitude in a cosmological eye blink. A civilization you dismissed as primitive 1,000 years ago, which is nothing on cosmic timescales, could now be consuming energy at rates that dwarf your own. You cannot afford to wait. You cannot afford to assess. The math does not give you time. Nick Lane at UCL proved this at the biological scale in his 2010 paper with William Martin in Nature, The Energetics of Genome Complexity. Lane showed that the endosymbiotic event giving rise to mitochondria provided eukaryotic cells with approximately 200,000 times more energy per gene than prokaryotic cells. That is not a typo. 200,000-fold. To put that in terms you can feel, imagine you are running a factory and your entire energy budget is a single AA battery. Now imagine someone hands you the output of a small nuclear reactor. That is the scale of difference between a bacterium and the cell you are made of. This single energy revolution, the incorporation of one bacterium inside another roughly 2 billion years ago, enabled the explosion of complex life on Earth. The mechanism is Peter Mitchell's chemiosmosis, for which he won the Nobel Prize in Chemistry in 1978. Mitchell proposed, against fierce resistance from the biochemistry establishment, that cells generate energy not through chemical intermediates, but through proton gradients across membranes. He was right. And the inner mitochondrial membrane, where this process occurs, generates energy at a density roughly 10,000 times greater than the sun per unit mass. Your cells are running hotter than a star, gram for gram. Lane's book, The Vital Question, published in 2015, made the full argument that energy, not information, is the missing variable in the origin of complex life. Without mitochondria, complexity was stuck. Bacteria can get big, like a Pulopicium fischelsoni at 600 microns, but only through extreme polyploidy, copying their genome thousands of times, which is energetically crippling. You end up with a giant cell that is metabolically no more complex than a tiny one, just bigger. Roughly 80% of a cell's energy goes to protein synthesis, each peptide bond costing at least 5 ATP molecules. Lane's work shows that even at the cellular level, energy gradients are the bottleneck on complexity. And the transition to eukaryotic complexity happened exactly once in 4 billion years. All eukaryotes on Earth share a single common ancestor. It was not gradual, it was an energetic revolution, an explosion in Cixin's framework, and it changed the competitive landscape of the entire planet. Prokaryotes went from being the only game in town to being the background, outcompeted, excluded from the niches that eukaryotes could now exploit. Gauss's principle playing out on a planetary timescale. The Carnot limit closes the loop at the top end. Sadi Carnot, who died of cholera in 1832, at age 36, after publishing a single paper, proved that no heat engine can exceed an efficiency of 1 minus the ratio of cold reservoir temperature to hot reservoir temperature. At the time, France was in an industrial arms race with Britain, and Carnot, a military engineer, wanted to understand the theoretical maximum performance of steam engines. He found it, and in doing so, he found a wall that applies to every energy conversion process in the universe. Consider a Dyson sphere, the concept Freeman Dyson proposed in a 1960 paper in Science titled Search for Artificial Stellar Sources of Infrared Radiation, a civilization so advanced that it surrounds its entire star with a shell or swarm of collectors, capturing every photon the star emits. Dyson himself later called the paper a little joke and clarified that he imagined a swarm of orbiting platforms, not a solid shell, which would be mechanically impossible. The inspiration came from Olaf Stapledon's 1937 novel Star Maker, not from engineering blueprints. But even a perfect Dyson swarm, capturing 100% of stellar output, cannot escape Carnot. The hot reservoir is the star's surface, roughly 5,780 Kelvin for a sun-like star. The cold reservoir is the cosmic microwave background at 2.7 Kelvin. That gives a theoretical Carnot efficiency of 99.95%. Astonishing, but not 100. The remaining fraction is waste heat radiated into space as infrared. A Dyson swarm would glow in the infrared like a lantern, which is exactly how we would detect one, which is exactly why no civilization has built one, at least not in our field of view. Nikolai Kardashev proposed his civilizational energy scale in 1964 in a paper on information transmission by extraterrestrial civilizations in Soviet astronomy. Type 1 harnesses the full energy resources of its planet, roughly 10 to the 16th watts, by Carl Sagan's later logarithmic interpolation. Type 2 captures the output of its star, roughly 10 to the 26th watts. Type 3 commands the energy of its entire galaxy, roughly 10 to the 36th watts. Current humanity sits at approximately 0.73 on Sagan's scale, roughly 3 orders of magnitude below Type 1. We are infants, energetically speaking, but even a Type 3 civilization commanding 10 to the 36th watts faces the Carnot limit. It still generates waste heat. It still operates within the Bekenstein band. It still competes for free energy gradients with any other Type 3 civilization in the same galactic cluster. The pressures do not diminish with scale, they increase. Because the energy rate density increases, the information processing demands increase, the Landauer costs increase, and the thermodynamic waste increases. Advancement does not buy you escape from the dark forest. It buys you a seat at a more dangerous table. The walls are not technological. They are physical, and they do not move. We started this with a question about aliens, about the silence of the cosmos. But the silence between stars is just the most dramatic instance of something that operates everywhere. The dark forest is not a place. It is a principle, and you have been inside it since the first cell divided, since the first neuron fired, since the first thought competed with another thought for the energy to exist. We are almost at the end now, and what is waiting there is worse than anything about aliens. In 2024, Amedeo Balbi and Manasvi Lingam published a paper in Astrobiology titled Waste, Heat, and Habitability. They demonstrated with straightforward thermodynamic calculations that any civilization with approximately 1% annual energy growth will render its own planet uninhabitable within roughly 1,000 years due to waste heat alone, not carbon dioxide, not pollution, not any specific byproduct of any specific technology. Waste heat, the irreducible thermodynamic byproduct of any energy conversion process, regardless of source. Solar, nuclear, fusion, zero-point antimatter annihilation. Whatever you invent, the second law guarantees waste heat, and waste heat accumulates. 1% annual energy growth sounds modest. It is roughly the global average over the past century. If you maintain that rate for 1,000 years, your total energy consumption increases by a factor of roughly 21,000. The waste heat from that consumption, which cannot be eliminated or reduced below the Carnot limit, eventually exceeds the planet's ability to radiate it into space. The surface temperature rises, not because of greenhouse gases, because of raw thermal energy that has nowhere to go. The planet becomes uninhabitable on thermodynamic grounds alone. Balby and Lingham calculated the timescales precisely for different growth rates and starting points. At 1% growth, roughly 1,000 years. At 2%, roughly 500. At 3%, roughly 350. The timescales are short by any civilizational measure, shorter than the history of Western civilization, shorter than the time between the Roman Empire and today. Their paper identifies 3 possible trajectories for any technological civilization: extinction by overheating, transition to permanent zero growth, or expansion into space to radiate the waste heat across a larger surface area. Each of these has dark forest implications. Expansion means becoming detectable. Zero growth means stagnation in a competitive universe. Extinction means the problem solves itself. There is no fourth option. The thermodynamics is airtight. Every civilization in the universe, whatever its biology, whatever its technology, whatever its values, faces this same trilemma: grow and become a target. Stop growing and become vulnerable. Overheat and die. A related paper by Michael Wong and Stuart Bartlett, published in 2022 in the Journal of the Royal Society Interface, showed that energy consumption scales superlinearly with population using urban scaling laws first identified by Geoffrey West and Louise Bettencourt at the Santa Fe Institute. The growth trajectory of any civilization is inherently unsustainable on physical grounds. They called this asymptotic burnout. The alternative, homeostatic awakening, a transition to sustainable equilibrium, would make a civilization essentially undetectable, which is another way of describing the dark forest. The physics forces you to either burn out, hide, or expand into territory where you encounter other civilizations facing the same pressures. There is no path that leads to a visible, stable, peaceful interstellar civilization. The physics forbids it. And then there is what Kansu Fidan called the Jevons filter in a 2026 paper in the Comparative Civilizations Review. The Jevons paradox, first described by William Stanley Jevons in 1865, the same year Clausius coined entropy, states that improvements in the efficiency of resource use tend to increase rather than decrease the total consumption of that resource. Better steam engines did not reduce coal consumption. They made coal more useful, which increased demand. Fidan argued that this creates a self-reinforcing feedback loop for any technological civilization. The more efficient you become at using energy, the more energy you use. The more energy you use, the more waste heat you produce. The more waste heat you produce, the closer you get to the thermal limit. Efficiency does not save you. Efficiency accelerates the problem. The Jevons filter may prevent any civilization from ever reaching Type 1 on the Kardashev scale. This is not game theory. This is thermodynamics. The dark forest is not a strategic choice. It is a physical constraint, and it operates at every scale, not just between civilizations, between any organized structures competing for thermodynamic gradients. Cancer is competitive exclusion at the cellular level. A mutation produces a cell that is marginally more efficient at extracting energy from its local gradient. That cell replicates faster. It outcompetes the surrounding tissue, not through malice, through thermodynamic advantage. The tumor is a dissipative structure, borrowing free energy from the same gradient as the body it is destroying. It is Gauss's paramecium aurelia, 5% more efficient, and that 5% is a death sentence. What makes cancer so terrifying and so illuminating for our purposes is that the cancer cell and the healthy cell are in the same body, sharing the same gradient, using the same biochemistry. The cancer cell is not an invader. It is a competitor that emerged from within. It was one of you until it found a slightly better strategy for exploiting the local energy supply. The dark forest, operating inside your own skin. Invasive species are competitive exclusion at the ecological level. The brown tree snake in Guam, introduced accidentally after World War II, drove 10 of 12 native forest bird species to extinction, not by outrunning them or outfighting them in any dramatic sense, by being a more efficient predator in an ecosystem that had no evolutionary experience with snakes. The cane toad in Australia, introduced in 1935 to control beetles in sugarcane fields, spread to cover over 1.2 million square kilometers and poisoned native predators that attempted to eat it. Zebra mussels in the Great Lakes, arriving in ballast water from the Caspian Sea around 1988, filter water so efficiently that they fundamentally restructure the entire aquatic food web. Each one a dissipative structure that exploits a local energy gradient more efficiently than the native species. The result is always the same. The native species is excluded, not by aggression in any meaningful sense, by thermodynamic superiority, by being 5% better at turning a gradient into copies of itself. Neural Darwinism, the framework proposed by Gerald Edelman and extended by subsequent researchers, suggests that neural circuits in your brain compete for activation. The patterns that fire most efficiently in response to environmental stimuli are reinforced. The patterns that fire less efficiently are pruned. Your thoughts are in a dark forest with other thoughts. Every memory that persists does so at the expense of other possible memories that were excluded from the finite information capacity of your neural architecture. Every skill you master comes at the cost of skills you did not practice. Every language you speak fluently slightly crowds out other languages. The brain has roughly 86 billion neurons and maybe 100 trillion synaptic connections. And that sounds like a lot, but the Bekenstein bound applies here too. There is a finite information capacity, and everything in it earned its place by outcompeting something else. I want to be careful here to note that the extension of competitive exclusion from ecology to cellular biology to neuroscience to cosmology is an argumentative synthesis, not a single established theory. No paper has formally proved that competitive exclusion is a universal thermodynamic law. But the mathematical frameworks converge. The Lotka-Volterra competition equations that describe Gauss's paramecia and the selection dynamics in chemical reaction networks and the Darwinian dynamics in neural development all share the same mathematical structure. The substrate changes, the principle does not. And the fact that the same mathematics keeps appearing at every scale, from molecules to ecosystems to neural circuits, suggests something deeper than analogy. It suggests a common cause, and that cause is the second law. In 2023, a team led by Lee Cronin published a paper in Nature called Assembly Theory Explains and Quantifies Selection and Evolution. Assembly theory measures the complexity of an object by its assembly index, the minimum number of steps required to construct it from basic building blocks. When you combine that with copy number, how many copies of the object exist, you get a metric that can detect selection anywhere in the universe. Their key finding was that objects with high assembly index and high copy number cannot arise by chance. They require selection. And selection, at its base, is competitive exclusion. The more efficiently assembled variant dominates. The paper bridges physics and biology by providing a measurement that does not care whether the competing structures are molecules, organisms, or civilizations. Selection is selection. Competition is competition. The gradient does not care what is competing for it. And this is the deepest implication of the dark forest theory, the one that Liu Cixin, for all his brilliance, stopped one level short of stating explicitly. The dark forest does not describe a relationship between civilizations. It describes a relationship between any organized structures competing for finite thermodynamic gradients in a universe governed by the second law. The universe does not create life and then threaten it. The creation and the threat are the same process. The thermodynamic pressure that drives the emergence of complex dissipative structures is the same pressure that guarantees those structures will compete. Prigogine proved that far from equilibrium energy flows create complexity. England proved that self-replication is thermodynamically favored. Cixin measured the exponential acceleration of energy rate density through cosmic history. Lane showed that even the leap to cellular complexity required a 200,000-fold energy revolution. And Gauss showed, 9 decades ago, that two structures exploiting the same gradient cannot coexist. Boltzmann saw it first. 1886, the struggle for entropy, not for energy, which exists everywhere as heat, for the gradients that make energy useful, for the thermodynamic slopes that allow work to be done and information to be processed and structures to be maintained against the relentless, mindless, patient dissolution of the second law. I spent a long time trying to find a way out of this argument. Some loophole, some escape hatch, some reason why the dark forest might not hold at the scale this evidence suggests. I looked at niche differentiation, the ecological mechanism by which competing species can coexist by partitioning a resource. Maybe civilizations could coexist by partitioning energy gradients, but at cosmic scales, the gradients are stars. You cannot share a star's output the way two bird species can share a forest canopy. The physics is too concentrated, too zero-sum. I looked at cooperation, the idea that organisms sometimes benefit more from mutual aid than from competition. But cooperation requires communication. Communication requires information processing. Information processing requires energy. And at interstellar distances, the costs outweigh the benefits by light years. Literally, I looked at the possibility that the universe's energy budget is so vast that scarcity never actually bites. But Bowlby and Lingham's waste heat calculations close that door. Even with abundant energy, the waste heat problem makes unlimited growth physically impossible within 1,000 years. I kept looking. The physics kept winning. And here is the part I keep coming back to, the part that I find most difficult to sit with. You are not an observer of the dark forest. You are a participant. You are a dissipative structure, a temporary eddy of low entropy borrowing free energy from the gradient between a 4.5 billion year old nuclear furnace and the 2.7 Kelvin void of intergalactic space. Every breath you take is an entropy transaction. Every thought you think costs kT log 2 per erased bit, minimum, paid to the environment as waste heat that slightly, immeasurably, but physically warms the universe around you. The gradient will not last. The sun will exhaust its hydrogen in roughly 5 billion years. The stars themselves will burn out. The gradients will equalize. Entropy will reach its maximum. And every dissipative structure, from the simplest convection cell to the most advanced civilization the universe has ever produced, will be excluded, not by a competitor, by the gradient itself, by its absence. But that is the long game. On shorter timescales, the game is the one Boltzmann described and Cixin dramatized. Multiple structures, finite gradient, thermodynamic selection. The more efficient dissipator persists, the less efficient one does not. The Fermi paradox is real. The silence of the cosmos is real. But it is not the most important instance of the dark forest. It is merely the most dramatic. The most important instance is the one operating right now, at every scale, in every system that maintains order against entropy, in the competition between species for ecological niches, in the competition between cells for metabolic resources, in the competition between neural patterns for representational space, in the competition between you and every other dissipative structure drawing from the same finite, dwindling, irreplaceable gradient. Cixin grew up during the Cultural Revolution, watching institutions of knowledge and culture systematically destroyed. His father lost his position because an uncle had fought for the nationalists and was sent to work in the coal mines of Yanquan in Shanxi province. Young Liu was shipped to live with grandparents in rural Henan to escape the violence. He has said that as a child he witnessed things that made him understand the complexity of human nature and the danger lurking in civilization's future. When things calmed down, his father maintained a wooden box of forbidden foreign books, and Liu read science fiction by flashlight, in secret, in a country where the wrong book could destroy a family. He grew up to study engineering. He got a job at the Nianziguan coal power plant, maintaining computer systems. The author of the most famous space opera of the 21st century spent his days in a provincial power station, watching energy extracted from 300 million-year-old fossilized sunlight and converted into electricity and waste heat, gradients being consumed, entropy being produced, the dark forest playing out every day on the factory floor. An anecdote that may be apocryphal holds that he once lost his entire monthly salary, 800 yuan, at mahjong, and quit gambling to write fiction instead. Whether true or not, the man who understood scarcity and survival not as abstractions but as the texture of his daily life had written something more precise than most physicists managed in peer-reviewed journals. In 2015, The Three-Body Problem became the first Asian novel to win the Hugo Award for Best Novel, and Liu became an international literary figure. But The Dark Forest was always the more important book, because The Dark Forest was the one that accidentally described physics. His two axioms are the second law of thermodynamics and the finitude of free energy, translated into the language of sociology. His chain of suspicion is Landauer's principle applied across light years. His technological explosion is Cicin's energy rate density, measured and published. His dark forest is Boltzmann's struggle for entropy, generalized to all organized complexity. The dark forest was never fiction. It was always physics. And physics does not care whether you have read the novel or understand the equations or accept the implications. The gradient does not negotiate. The second law does not make exceptions. The Bekenstein bound does not expand to accommodate your civilization's ambitions or your species' hopes. I keep thinking about Boltzmann, about a man who saw deeper into the nature of reality than almost anyone alive, and who was punished for it by the very institutions that should have celebrated him. He looked at the equations and saw war. Not war between nations or species, but war between organization and dissolution. A war that every organized structure in the universe is fighting every second of its existence, and that every organized structure will eventually lose. He saw it in 1886, stated it clearly, and the physics community spent the next 20 years telling him he was wrong about whether atoms were real. He died believing he had failed. He had not. He had simply been too early. And I keep thinking about Landauer, about an 11-year-old boy on a ship to New York carrying a dead father's wish that he grow up to be a good German, learning a new language, building a new life, and eventually discovering that the universe charges you for every piece of information you forget. That forgetting is not free, that the erasure of any record, any memory, any identity leaves a physical trace in the heat of the environment. The universe remembers the cost of forgetting, even if we do not. And Beckenstein, the graduate student who told Stephen Hawking he was wrong about black holes and turned out to be right, who wore a kippah in physics departments and said the universe was the product of God, and spent his career discovering that information has a ceiling, that even the universe's capacity to know things is finite. These are the people who found the dark forest, not in fiction, in equations, in experiments, in the irreducible mathematics of entropy and information. And their work has been sitting in the literature, cited thousands of times, taught in every graduate thermodynamics course, used in every information theory textbook, and nobody put it together. Nobody said, wait, if energy gradients are finite and information is physically costly and competitive exclusion operates at every scale, then the silence of the cosmos is not a mystery. It is a prediction, the most obvious prediction in the history of physics. And we missed it. For 140 years, we missed it. You are in the forest right now, not as a metaphor, as a thermodynamic fact, a dissipative structure, temporarily organized, burning through a gradient that took billions of years to establish and will not be replenished when it is gone. The question was never, where is everybody? The question was always, what happens to everything that borrows energy from a gradient it cannot own? And the answer is the same at every scale, from paramecia to civilizations, from neurons to galaxies, from the first convection cell in the first cooling pool of matter after the Big Bang to the last red dwarf burning its final hydrogen in a universe going cold. The gradient is consumed, the structure is replaced, and the entropy of the universe moves as it has always moved, as it will always move, toward its maximum. Boltzmann saw it, and it killed him. Schrödinger named it, and moved on to other things. England proved it, and became a rabbi. Cixin wrote it as fiction, and won the Hugo. The rest of us are still in the forest, still borrowing, still burning, still competing for the same light, the same gradients, the same dwindling thermodynamic potential that every organized structure since the first atom has needed and fought for and eventually lost. That is not a theory about aliens. That is the universe telling you what it is.